Very good morning, students. As you all can see, today I have combined section A and C. Right, so I'll be taking both my classes in this period, right? So for section C, I want to say that basically Monday was a holiday, because of which I had missed the first class in your section. So for the rest of the sections, basically I had started with DFA minimization, and I had explained one method, the equivalence theorem for minimizing a DFA. So since you all have missed that class, I'll go back to that in the later classes. Like I'll cover that portion in the next week. For today, that is for today's class, I will explain, or I'll start with the second DFA minimization method, that is Myhill Nerode theorem. That is, how can we minimize a given DFA using the second approach, right? So before moving into that, just to remind all of you, yesterday only I had a class with section A where I had discussed the method for minimizing the DFA using equivalence theorem, and I had also mentioned that why is minimization required, because obviously we will always want that we represent a present system with a, or we can model a present system with a minimal number of states using a DFA, right? So like the lesser number of states, the more optimal is the solution. So obviously we will try to minimize the DFA as much as possible, keeping its functionality intact. And for the same, we have two processes. One was equivalence theorem, one was Myhill Nerode theorem. So in today's class, we are going to discuss the Myhill Nerode theorem, and then we will, maybe if time is there, we will be moving on to some other topic, right? So let me share my screen. My screen is visible, students, right?
Yes, it is.
Yes, ma'am.
Oh, thank you. So yeah, as I was saying, the second method, the table filling method on Myhill Nerode theorem for minimizing a DFA. Again, you can go through the steps from this PDF whenever you want to. I'll directly come to the example. This is the given DFA to you. As you can see, there are 5 states, out of which this one is the final state. E is your final state, right? Now coming to the process. The first and foremost thing that you need to do is you have to construct a kind of a table. Now this is already done over here. Still, I'll go to the canvas and do it for you. So here we have 5 states, as you can see, A, B, C, D, E. So with respect to these 5 states, we have to construct the table. Okay. So how would the table look like basically? So I'll write the name of the states at the top. Okay. And I'm going to write them on my left hand side, that is both row wise and column wise. I'm going to write the name of my states. Fine. Just trying to create a table kind of a structure. Okay, so now we have each cells corresponding to each pair of states. Now start filling the table from the lowermost row. How to fill the table? Come to this point of your step, this one. Consider every state pair in the DFA where Qi is F and Qj like qi belongs to f and qj does not belongs to f, right? Which means that we have to consider, we have to mark every pair where one is a final state and another is not a final state. So for our DFA, which is the final state? E. So what are the possible pairs that we are going to mark? All the pairs containing E. So CE, BE, DE, AE. They need not be connected directly. That is not the issue. You have to keep one thing in mind, that the pairs that you are going to mark, that should contain one final state and one non-final state, and it should cover all such possible pairs. So going back to this, obviously I'll mark this, I'll mark this, I'll mark this, I'll mark this, and I'll mark this. Okay. Acha, one more thing, you have to disable some of the cells over here. How to disable them? See, we actually start from the lowermost row and see the combinations that we get. Like this cell is for AE, this is for BE, this is for CE, this is for DE. Acha, this one is blank, this one you don't have to consider, right? E you don't have to consider because it's repetition of the same thing. Similarly, see, DE, the pair DE has already been considered over here. So, no need to consider the pair DE in this row. So, just mark it as like this. Again, DD you need not consider. This is a,
Here we will just consider the portion below the diagonal, bottom, I
yes,
mean
yes, yes,
the
yes, yes, yes.
portion above the diagonal we can omit from the table.
Exactly. This three cells you are going to consider. Again over here, similarly, just ignore this one. CD, CD has already been covered in this row, so ignore CD. CE also has already been considered over here, CE. So just ignore this part. Here, ignore, 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 and here ignore all the cells, right? So only this portion you have to consider. Okay. Acha. Now the first step was marking the pairs where each state is final and another state is non-final, right? Now moving with the second step. What is the second step? In the second step, basically if you go to the steps that I have written, repeat this step until we cannot mark any more states. If there is an unmarked pair QI QJ, mark it if the pair QIA or QIA is marked for some input alphabet. Okay, so this is a bit confusing. The writing over here is a bit confusing. What I mean is, come to this table and we have already marked the lowermost row, right? Acha. Now try to understand one thing. You have to check this for all the present pairs. So suppose I start checking from the lowermost row. Okay, so what is the lowermost, what is the first entry in the lowermost row? The first entry in the lowermost row was ED or DE, whatever it is. So just check for where is the DE, yeah. So DE is already marked, fine, we do not have to check for it. Again, all these are already marked, so we will start checking from this pair, that is CD, if we can mark it or not. So how to do the checking for CD? Go to this, yeah. So for the pair CD, for input alphabet 1, where do we go? So D on getting a 1 goes to E. C on getting a 1 goes to C, right? Acha. Again, you have to check the same thing for your input 0. So CD, CE on getting,
Basically here D comma A, D comma B, D comma C all will get marked because D on getting input 1 will
yeah,
be reaching to E,
yeah,
and all the pairs or all the states associated to E are already marked. So all the states associated with D, I mean D comma A, D comma B, D comma C, they will also be marked.
yeah. Basically, any state where you see that the next state is E, it will be marked. because E has already been marked. So any and every state which has got a next state as E, either on encountering a 0 or on encountering a 1, would go to would be a part of the marked state. So here we can see that CD, D on getting a 1 goes to E. So we can actually mark the pair CD. So here we can mark the pair CD. Again, why? Because D on getting a 1 was going to the state E, which was already marked, which is a part of the marked state. Acha. Next what we have? Next we have BD. The next pair is BD. Again BD also contains D, which will go to state E on getting a 1. So again BD will also be marked. So let us mark BD as well. Next is AD. So AD will also be marked because again D is here, and D on getting a 1 is going to E, which is already marked. So this will also be marked. Okay. Acha. Now finally what are the other possibilities? Once we are done with this one, the next row is this one. So let's check it for
And here
BC.
BC will also be marked because you see that B on getting on will be D, and now that pairs corresponding to D's D have been marked, so
Exactly.
BC will also be marked.
Exactly. So if we are going to check the same thing for BC, you see that B on getting 1 goes to D. So since D has already been marked over here, so BC will also get marked. So you mark BC as well. What about the other states? AC?
AB will also be marked, but AC will not
Yeah,
be.
AC won't be marked. Why? Because just a small checking. AC. So if you check for AC, the pair AC, it goes to B on getting a 0 and goes to C on getting a 1, which are not marked, right? So you are not going to mark the pair AC, right? So next we can check for AB as well. So if you check for AB, basically AB on getting a 1, that is B on getting a 1, it goes to D, and D has already been marked. So again AB is also going to get marked. So I repeat, for the pair AB, if you check, the B portion on getting a 1 is going to D, which has already been marked in the lower section. Therefore we can mark AB as well. And remember one thing, we actually do the processing from the lower row to the upper row. Just proceed from the lowermost row to the uppermost row. Don't break the sequence. Don't just jump from this row to this row. Otherwise the calculation will be will have some error. Okay, so go sequentially row wise and start from the lowermost row. So after the process is completed, we will see that we have all these marked pairs, and the only unmarked pair over here that we have is AC, correct? So basically whenever we have an unmarked pair, that can be combined together as a single state, and all the other state remains same as they were, right? If you follow the last step, combine all the unmarked pair and make them a single state in the reduced DFA. So here my unmarked pair is AC, and I have combined it as a single state, and all the other states are remaining as it is, that is B is here, D is here, E is here, right? And the transitions, again you have also seen in the previous class that transitions can be easily mapped from this DFA to this DFA whenever you
Ma'am, can you repeat the step 3, ma'am?
uh, which one Rohit?
Step 3, ma'am. Step
AB,
in
this
this.
one.
Yes, ma'am. From the first, ma'am, how you are selecting.
Okay, fine. So basically this is the diagram. Fine, this is a DFA given to you. Okay, the first step that I am following is I am marking the all the states which contain the final state. Okay, so this pair is AE. Just take the combination of the row and the column. So this cell stands for AE, this one for BE, this one for CE, this one for DE. So since they contain a final state and a non-final state, all the cells will be marked. This is your first step. This is clear, Rohit? Up to this it's clear?
Yes,
Okay.
ma'am. Yes, ma'am.
After that, what you do is you keep on checking the DFA. Go to the DFA and see that for the other cells that you have, what are the other cells you have? These are already marked. So the next cell that you consider is CD. This cell is for CD. So go and check for CD. What are you going to check? CD. C on getting a 1 remains at 1. Fine. D on getting a 1 goes to E. And here is your point. Since out of the pair CD, D on getting a 1 is going to E, which is already a marked state. CD is also going to be a marked state. So any such pair which contains a state which goes to some next state which was already marked will also be marked. Therefore, here we will mark CD. Why? Because out of this pair CD, D on getting the input alphabet 1 was moving to the state E, which was already marked in our previous step. Therefore, we will mark CD also. Similarly, BD, again same thing, D is a part of this. So D on getting a 1 was going to E, which was already marked. So we will mark BD as well. And same for AD, D is a part. So we will mark AD as well. Achha, next what do you consider? CB. Again go to the diagram. For CB, if you see the B part, it goes to the state D on getting 1. And D is already marked in my previous state. So D, in my previous step I have already marked D. So therefore I will mark BC also, because C on getting a 1 is moving to D, which was already marked in my previous step. Therefore I will mark BC also. Okay. What about AC? Check for AC. If you check for AC, AC does not have any such next state. So C on getting a 0 goes to B, C on getting a 1 goes to C, A on getting a 1 goes to C, A on getting a 0 goes to B. So none of the next states have been marked in the previous step, right? So so therefore your AC is going to remain intact. AC won't be marked because A and C both do not have any next states which were already marked. Okay. Acha. Finally, we have AB. So if you check for AB again, you will see that AB, for AB, B is going to the next state D on getting a 1, and D has already been marked by us in a previous step, right? So therefore the pair AB is also marked. See, we have also marked the pair
Okay,
AB.
ma'am. Okay.
The only unmarked state is AC. The only unmarked state over here is AC, and that is the state we are going to combine in our minimized DFA to get the minimized DFA, and that is exactly what we have done. We have combined AC as a single state and all the other state remains same, right? And this transitions can be easily checked from here. They remain same. Transitions are actually not altered. So just check one transition. The transition for this AC on getting a 0 is A on getting a 0 was going to B, C on getting a 0 was also going to B. So AC on getting a 0 will easily go to B. Again A on getting a 1 was moving to C, C on getting a 1 was moving to C itself. So we can easily put a self loop. And see, for all the rest of the states it will be easier because they remain unchanged. We already have all the states over here and here also, so just copy them out from here. So this is a process of minimizing a DFA using table filling method or Myhill Nerode theorem. Okay. So just to check whether you have understood the things properly or not, this is another DFA one. Actually, I don't know why it has moved here. Basically, this is state A, this is state B, this is state C, and this is state D. Okay, the C and D have moved here and there, sorry for that. So this is C and this is D. The input alphabets are 0 and 1. The final states are C, D and E. Okay, so you have to follow the same method and find out the minimized df. Okay, so basically if again we follow the same method, students, this is our table, and what are the final states? The final states are c d e. So all the rows or all the cells which contain a combination of either c or d or e will be marked in the very first step. So see, all the cells in c, uh, all the cells in d, and all the cells in e. Yeah, all the cells in e and d have been marked, right? So yeah, next what we have been
All the cells will not be masked because CD both CD are actually final states. So E comma C, E comma D, these cells will not be marked because then in that case E and C both are final states.
like I could understand. Tell me again, what did you say?
In the DFA, given DFA, there are three final states C, D, and E. Okay. So our criteria is we will mark only those
Yeah, yeah,
pairs. Let's say
one
mark
is
those.
final and one is
One
non
is
final.
final and one is
Correct, correct,
non-final.
correct, right, right.
So I cannot mark the states
ed,
like E
yeah,
comma
yeah,
C,
correct,
E
correct,
comma
correct,
D.
correct, yeah. So yeah, sorry I missed it. Basically because the criteria is one should be final and one should be non-final state, therefore any such entry where we have two final states cannot be marked. So suppose the pair CE or the pair DE or the pair CD cannot be marked. So if you see, if you check over here, the pair CD has not been marked, the pair CE has not been marked, because one should be final and one should be non-final. Okay, so this is the first step where you mark all the pairs containing C, D and E with one final state and one non-final state. So by like following that process, all the cells are going to get marked. Fine. After that, again you need to follow the same process and check whether any of the other states are basically well, moving to a next state which has already been marked, right? So here is a point that we can see that if we input 1 to the state A and F, it will go to state C and F respectively. C and F is already marked, hence we will mark the pair AF. So where is the pair AF? Here is the pair, this is the cell for the pair AF, and if we check for the pair AF, it goes to the state C and F. If you check the pair AF, it goes to C, and F also goes to sorry, A and F, right? So yeah, it goes to C and F, right? And the pair CF has already been marked. The pair CF is already marked, right? So because that A and F on encountering 1 moves to C and F respectively, and C and F has already been marked in the previous step, we can again mark AF in the present state. So we are marking AF, and again if we check for the pair BF, again you will see that suppose this is B, right? So B on getting a 1, it moves to C, and F on getting a 1, it moves to F. So the next states are again DF. So DF has already been marked, if I am not very wrong. So since DF has already been marked, we can mark BF. Okay, and for all the other states, I guess if you check, you can see that no more marking is possible because we are not moving into any next states which has been marked in the previous steps. So here what are the unmarked states? The unmarked states are CE and DE, and over here it's CD. So CD, CD, CE and DE. We are going to combine these three pairs, and we will get if we try to draw the reduced DFA, basically it will look like this. So we have CE, we have CD. I'm just writing down the states, okay? And what else was there? We had CD, we had CE and DE, CE and DE, right? So CE and CEDE, and CD was there, and all the other states would remain same. What are the other states that we had? We had A, B, and F, right? So for A, B, and F, just we can write A, B, and we have F. So now this basically these are the new states of your minimized DFA. So is there any reduction of states? 1, 2, 3. We had 6 states. Over here also we are having 6 states. So
C, D, and CD can be combined and be written as a single state CD.
wait. So let me check the combine all the unmarked states and make them as a single state and reduce DFA. So if we are having CE, DE, and CD, right? So basically, yeah, all of them can be combined together because they are interconnected combinations, right? So what we can do is we can write a single state CD. So we can write a single state CDE, and all the other states would remain same. I guess A would be the starting state and the CDE, this is going to be your final state. Transitions can be easily checked from here, from the given DFAs. I am not putting the transitions, but the final DFA would consist of 4 states, that is the reduced DFA would consist of 4 states, A, B, F and CD. Okay. So basically this is the process of minimizing DFA using your Myhill Nerode theorem. Okay. So any confusions?
Yeah, I had one confusion. Can you just go to the tick marks? I mean, the why the tick marks are given? Yeah, so you can see that here the unmarked pairs are A comma B, then D comma C, then E comma C, and also A comma F, B comma F are unmarked. So shouldn't I combine A and B?
Why should you combine A and B? Like the final, see, look at the final table and tell me.
Watch, look at the final table here. You can see that here the unmarked states are what? Unmarked states are A comma B, D comma C, E comma C, and E comma D. So we are combining D comma C, E comma C, and D comma E, and I am writing it as a single state D comma C comma E. But A comma B itself is also an unmarked pair. So
Actually,
I
wait,
should
wait.
write it A comma
Yeah,
B as a
wait.
pair.
So CD was unmarked, CE was unmarked, DE was unmarked. That is fine. And over here AB was, yeah, AB will all, I had actually missed that AB was not marked. So yeah, AB will also be combined. But I have, yeah, but I
No,
have a confusion over here. Basically, I have to check whether CDE can be combined to a single state or they'll remain separate. That I have to check. I am not very sure.
CD actually, can you please go to the DFA given DFA
Yeah,
diagram?
1 second. So basically, we are having something like this according to whatever we have got till now. AB is there, CD is there, and F is here, right?
Yeah,
Yeah.
it is.
So, yeah.
Yeah, so whether CD can be combined or not, we can check from the diagram. You see, from C, if I go, if for C, if I give 0, I will go to E.
Hmm.
If I go 1, I will. If I give 1, I will be going
Hmm.
to F. For D, if I
Yeah,
give
yeah, yeah.
0, I will be going to E. So that means C comma D comma A. If I give 0, it will be a self loop
It
on
will
C
be,
comma
yeah,
D comma A.
obviously it will be a self loop, and for E,
And
for
if I
1
give 1, it
it
will
will
be
go
F.
to F. All of them are
Yes,
converging to F.
yes.
So logically it should be combined actually, C, because we are getting all the pairs. We are getting CD, we are getting CE, and we are getting DE as well. So I think it is because basically, the last step, it's literally not very clear, because combine all the unmarked pairs and make them a single state in the reduced DFA. So like, can we combine more than one state? Logically we can combine it over here, because by looking at the DFA, obviously it can be easily combined, but I think it is possible, won't be a problem.
Yeah, it
Yeah.
is possible.
And yeah, AB I had missed, so AB will also be, obviously AB will be combined, because AB is a unmarked state. So finally, therefore, we get these three states, C, D, A, B, and F. So something which had six states, that has been converted to or minimized to three states. Okay.
And one more thing, if I there are two methods. One is the
Mm-hmm.
equivalence theorem, and one is the civil filling
Mm-hmm.
method. So if I apply both the methods, will I get the
Yeah,
same
yeah.
result or different
Logically, you
result?
should always get the same result. You should always get the same result.
Yeah, right. Okay, okay.
Okay. So this was all about minimization. I had a few small topics left which I wanted to discuss basically. So this thing you all might be knowing, but still I thought of discussing that what is a complement of a DFA. Sometimes you might be given in a question that this is a DFA you have to design, and after designing, please draw the complement of the DFA. So the complement of a DFA can be obtained just by swapping its accepting states with the non-accepting states, right? So if this is the DFA for a language, first of all tell me, this DFA accepts which kinds of language. But just looking at the DFA, which kinds of languages
AB.
are accepted by the DFA?
Same AB.
Is it,
A.
look at it carefully, is it AB? Because this is a final yeah, it's a final state. The Z is a final state. So it's an initial state. You move to the final state, you get A's. After that, all are basically trap states.
No, only
Only
A,
A,
ma'am.
like,
Man, basically
huh,
it accepts the
A plus.
language which ends with A.
Yeah, it starts with A, ends with A. Yeah, it's A plus, basically A plus closure. Okay, minimal string is A, and after that any repetitions of A. Hmm. So if you are now asked to find the complement of this language, or sorry, I should say the complement of this DFA rather, you just swap the uh, accepting state and what non-final and the final states. So the initial state remains same, but x and y will become the final states, and z will become the non-final state. And now if you try to derive the kind of languages accepted by the DFA, you will see that it accepts a language such as it starts with B, or it starts with A and it's followed by a B, or yeah, these two variations are possible. Basically, if you see this portion, it is starting with B followed by any combination of A or B, and here it starts with A followed by B. So if you think logically, basically the language is also the complement, because the previous DFA was something which just contained A, like it would start with A, end with A, it will contain A, and here it can firstly it can start with B. Secondly, even if it starts with A, it will end with B. Okay. So this is how we can easily find the complement of any DFA, and from that you can also understand the complement language of that language, right? So this was one thing I wanted to discuss, and this is a small question for you all, very easy. So consider the given DFA. This is a given DFA. Okay. So which of the following is false? So three options are given. Complement of LA is context free. for the language accepted by A is the minimal DFA, and A accepts all the strings over 0, comma 1 of length at least 2. So see, till now we have not like gone for context free. So let's avoid this option and first check option 3. A accepts all strings over 0, comma 1 of length at least 2. So it is it true?
No,
No,
not
ma'am.
at
It
least
can
two.
accept
Yeah,
zero
it can
also.
accept
Zero.
0
I
also. So
mean,
number 3, option 3 is false, right? Now checking for option 2, for the language accepted by A is the minimal DFA. Now this is also
yes,
false.
ma'am. This is true.
This is not true basically, because for all the people who had done the like yesterday's class, the equivalence method, it will be a bit it will be a bit fast to do with equivalence method, because the very first step of the equivalence method will be partitioning it into Q2 and Q0 Q1. If you remember the partitioning method that I had teach you all last day, so we actually used to partition it in such a way that the final state will be in one portion and the non-final states will be in other in other portion, right? So I guess this is not the minimal DFA. The minimal DFA will contain two states.
But ma'am, if you just look at the example here, there are three states. So in the first, P0 partition will be Q0, comma Q1 and Q2. There will be two sets. Okay. But from there you see that we have to check. Q2 is a single state, so I don't need to bother about it. I need to check whether Q0 Q1 can be separable or not. But you see, Q01 getting to 0 is going to Q2. Q1 getting to 0 is going to Q2. Now in the P0 transition, both Q2 is in the same state. I mean, both are going to the
Hmm.
same state. And if you check for one, Q0 going to 1, for Q0 for 1 going to Q1, Q1 also going to Q1 for going on for
Hmm.
1. That means that is also
Hmm.
same state. So that means you cannot distinguish Q0 and
Exactly.
Q1. So I think that is a,
Therefore, there,
so that is I think the
yeah,
minimal DFA.
exactly. Therefore, in the minimal DFA, we will have two states, not three states. In the option 2, it is said that for a language accepted by A is the minimal DFA. This is not the minimal
Oh yes,
DFA.
yes, yes, yes,
That is what I am
yes, yes,
saying.
yes, right. There will be
There will
two
be two
states. Two
states.
states will be
Now
there.
you can also try
Yes,
it
yes,
with
right.
your Myhill Nerode theorem, whatever I have taught you all, because for section,
No, no, it will be
yeah,
easy
it
with
will be easy
equivalence
for
theorem.
equivalence theorem, and for section C, don't worry, I'll cover it in the next class, your equivalence theorem. So basically, what with whichever method you try, you will see that this is not the minimal form, and you can minimize it with two states, right? So both option 2 and 3 are not correct, and I am not going to, even if you go to the option 1, you already know right now that we can complement a DFA, and obviously if we can complement a DFA and get another DFA, so a DFA is something which is for regular language, right? What we have learned till now, a DFA is for regular language. So if we can complement a DFA and get another DFA, then why should it be context free? It should be a regular language. Like whenever we are able to construct a DFA for a language, that language needs to be regular language. It need not be a context free language. Okay. So since we can easily complement it by swapping the final and the non-final states, whatever language we will get, since it's a DFA, the language will also be a regular language. Okay. Someone has written something maybe in the chat box. ENCRP answer. I have to check what is the question, Satya. Please wait for some time. Uh, I'll check it after I finish the class. Okay. Okay. So this is done. Acha. One another important thing that should be known to all of you, because a huge part of regular language is completed. What is left is regular expressions that maybe I'll cover in the next week. I'm not very sure, but you should be well aware of the closure properties of a regular language. Now, what are the closure properties? These are some operations which, when done on a regular language, uh, we have to check whether a regular language is changed or it remains a regular language. So when it remains a regular language, we say that the regular language is closed under this operation. So a regular language is closed under clean closure. Okay, so clean closure, all of you remember what is clean closure? I have discussed clean closure in the very first class. That is the alphabet set star, which contains all the possible
The
combinations.
actual
Yeah,
star,
yeah, it contains all the possible
sigma stars,
combination. Exactly, sigma star. And then positive closure was sigma plus.
plus
Complementation, it is a regular language we have just seen. Union, intersection, difference, reversal, all of these are union. Means if you do the union between two DFAs, the resulting whatever you get, the resulting thing will be a DFA, and the language generated by that will be a regular language. Intersection also same. If you do the intersection, it will be a the resultant will be a regular language. Difference also same, and reversal also it will be same. Okay, reversal means just reversing the direction of the what is that, transitions. Reversing the direction of the transitions, and the DFA that you get, it is also